right, so yeah, so thanks everybody for coming out. I think I've had a very interesting few days. Hopefully everybody has as well. I do appreciate that we come at quantum optics and cavity QED from lots of different perspectives, and I think to the extent that we can cross-pollinate each other's ideas, that's very helpful, helps move the field forward. So what is the field? I guess that's what this discussion is about. So I've been encouraging everybody to contribute some their own perspectives on the big physics ideas, the big opportunities that stand before us in the area of many-body cavity QED or many-body quantum optics. Some of you participated in my assignments, so thank you for that. Many of you didn't. And, okay, so I'll say two things. One is, for those of you who are shy about exploring these kinds of big ideas, let me encourage you to do so. You know, we're the dreamers, so we have to give ourselves permission to dream, to think big thoughts. I know everybody's very concerned with, you know, the specific thing that they're working on in science, but you want to have some kind of broad picture to know why it is you're pursuing it. Maybe you'll really create something new. It was maybe suggested to me last night that in the choice of two methods, the carrot or the stick, I was using the stick approach too much, that I should have offered more carrots.
Carrot cake, I said.
There you go. Carrots. Good. All right, so now I can dismiss that criticism. Okay, so here's what folks came up with in this spreadsheet that we were developing. I think many of us are imagining cavity QED in a many-body setting in terms of what it can do for us. So we have maybe some ulterior motives for things that we want to create, and we're wondering how quantum optics as a method, even as a technology, as an engineering tool, can get us to where we want to go. So one perspective I have is that condensed matter physics is often about preparing. So in condensed matter physics, theoretical condensed matter physics, we think about some many-body quantum model. And then we ask, well, what's its low energy, or maybe what its ground state? And if you stop, you realize that often what we're more interested about is the state, not the model, not the system. The system and low temperature is just the means by which we create the state. So, you know, the quantum Hall states, for example. So maybe we should be state-focused and ask, okay, well, if we just want the state, how should we best prepare it? And so there's this question about whether things like feedback through the cavity fields, feedback through something that the state preparer is doing, can create states that are of interest to us. Dissipation is, of course, part of that. So many-body cavity QED is about open quantum mechanics, and so we know examples where, say, optical pumping, dissipation can produce states that are of interest to us. So also connected to Monica's talk earlier at this meeting, we asked, you know, what are the bounds of what you can do using dissipation in some creative way? So there was the idea of putting a frequency structured pulse onto a cavity filled with atoms, or equivalently a temporally structured pulse, and that might create something that is new. It's a question about also the fidelity of this method, and, you know, of course, you want to know how good it is that you prepare the state of interest. So that it bears to examine this, I think, a fair bit more. Here was an interesting correction. So quantum error correction is the the gate-based quantum computing method for steering a quantum system to evolve in a particular way in spite of disturbances that it's subject to. So I love this idea of asking ourselves to what extent these ideas will apply in a more general setting. So if we're aiming toward preparing a state, maybe that's just a guide as to what sorts of dissipation we should be considering, but maybe quantum error correction is going to inspire us for the right kind of dissipation or feedback that'll, even in a continuous system, will get us toward, not just a digital system, will get us to where we want to go. somebody suggested a quantum thing with a B, Brontosaurus, and wanted to know whether that was a way to transfer a quantum state from one state, a quantum system from one state to another. So anyhow, this goes in the same category. It's just a word that I don't recognize. And then, and this is then a specific version of this kind of state preparation. If I have, maybe related to Dave Schuster's efforts, if I have a spin or maybe a few spins and they're interacting within a system, that's sort of my highway. That's the in and out. So can I use that as the one conduit to kind of figure out how to prepare states or instill some sort of correlation and entanglement within a many-body quantum system? I think that's a fabulous idea. And also, as we keep studying that few-body system that is embedded within a larger system, what do we learn about that larger system? We have such great control over it, we can also see how it's influenced by the system. I'd say many of us are also inspired by the, I would say, somewhat hackneyed idea by now of creating quantum simulators of many-body quantum systems, but we're wondering what really novel stuff can we get when we have quantum optics and multi-mode light and all of that. So that's stated here, and here in particular, I like this emphasis on quantum light. So not just the classical wave mechanics that Andreas was dismissingly discussing, but also the quantum fluctuations of such fields and what does that give us. I think we've talked about how we can get long-range interactions and also retarded interactions and all sorts of maybe new tools. So I wonder what kind of interactions can we generate in a general sense using these methods that may be rather unnatural, that maybe no one would ever have even thought of because it just seems so unphysical. Why would you ever make a many-body quantum system that is described that way? The idea of structure, pattern formation, glasses, things that Ben has been thinking about. So I think that's a really new direction for quantum optics to consider, what that means in terms of all the photon physics. Optomechanics obviously has been building toward that, sort of a single mode stepping stones, but ultimately one maybe is talking about a really complex system that is undergoing mechanical responses to quantum fluctuations of light. This is maybe our tool toward structural phase transitions to be studied in a let's say a cold atom context, or I would say similarly a self-organization within a circuit QED setup as well. That's all possible. And okay, so I listed a few of the ideas that came up in that regard. And then I think the work in Zurich is sort of encouraging us to look in detail at phase transitions that are occurring within the microscope of a quantum optical system in order to understand that kind of physics with greater detail. The dynamics of many-body quantum systems, in particular ones that are being driven externally, is really interesting. It's really open and is sort of it's really what this field is going to produce. I have my own doubts how much sort of equilibrium physics we should be studying using cavity QED setups. That's not their natural state. Their natural state is that they're being driven and fluctuating. So if you wanted to point to the strengths of that system and the features of that system, maybe we should be looking at both open and closed dynamics within many-body quantum systems. There's good questions in general about many-body quantum systems and whether they thermalize, and I wonder what novelty comes out when we have also an open system in that regard, maybe subject to feedback. Okay, so that was stated here. We've studied a lot in many-body quantum systems how things evolve toward thermal states, but I think in steered or fed-back systems, a complex system is going to evolve toward a non-thermal state, some kind of state that's stabilized by feedback. And so one can ask similar questions, but now about these driven dissipative systems, and there may be subtle distinctions to be made there. And then I think this is like a pretty far out goal, but I love how far out it is to understand how strongly coupled quantum systems thermalize, and whether the bounds set by strange gravitational theories have anything to do with physics. I think from Igor's talk there was a discussion about physics systems that are evolving under measurement, sometimes weak local measurement. We can also think about non-local collective measurements, and how does that influence dynamics and transport properties, I think is very interesting. The concept of phase transitions in driven dissipative systems came up several times during the conference. There were the dissipative phase transitions, there were dynamical phase transitions. I don't know what else is going to occur. So I think that this is all fairly interesting. We had a question from Peter's talk about whether some kind of universality is achieved in the Zurich experiments or not, and that's a more general question. Also, in a time-driven system, order parameters need not just be things that are defined in space, but they can also be defined in time, such as in this example of discrete time crystals. So we can ask, in a broad sense, what new types of order parameters might be achieved in a time-evolving quantum system. Not just that it's periodic in time. That's one type of order, but there's probably other types of order as well. And then I very much appreciated Andreas Wallerhoff's response to my pesky question when I asked him about his double quantum dot experiments, what new physics I'll hand these slides out. There's nothing to do about this. What new physics are you getting by sticking a squid loop on this thing? And he said, look, I have this super quantum sensor that's now sensing condensed matter, and it lets me study a condensed matter system and thereby dispel some of the superstitions that we had about what governs these systems. That's perfect. That's a perfect response. So I very much think that embedding these, and we saw it also in Dennis's talk, that placing quantum optics within real materials allows us to study those materials, and I think is going to lead to direct breakthroughs in material science, not just through simulation, but through examining them directly. There's also ideas out there for, let's say, Floquet physics, which we've explored a lot in cold atom systems, but also has been imagined to occur in graphene, let's say. So we can ask, when real materials are brought into the fold of what we apply many-body quantum optics to what extent can we just extend those ideas into a sort of real material setting instead of the very artificial materials that we're busy creating. So that was sort of what I gleaned from that spreadsheet and the perspectives that you added so far. I'll welcome you to continue these discussions amongst yourselves on the flights home when you get back to your home institutions. If you want to keep contributing to this spreadsheet document, please do so. I don't imagine any of you will, but hey, maybe somebody will. And again, so let me thank all of you for your participation, but let me in particular thank, again, the people that made it happen. So Hussein and Naomi, they've been they've been contributing and also in orbit around this meeting constantly, and this meeting has been a great example of what ITAMP is doing in the service of the broader scientific community, and we're very, very grateful for all that you, all the time you put in, all the organizational skills that you have that we lack. So let's all thank them heartily for their help. And to express our gratitude, we have bought several dozen pizzas, and we invite you to eat them all at your leisure. And I also want to thank Murray and Ben, who helped out with planning out this endeavor. And we came up with a pretty good speaker list, it turned out, and I think we pulled together a pretty stimulating meeting. So
Big hand for Dan.
Big hand.